When this type of reaction, neutralization means forming something that is neutral. What do you think is neutral that we're going to be forming?
Water.
Water, most likely. So we have an acid and a base that come together. And what kind of reaction actually is this of our 5 types of reactions? So it is aqueous all the way, but we have 5 types of reactions. We have synthesis, we have decomp, we have single replacement, double replacement, and combustion. Which of those does that look like? That is double. You see them switching partners? That's all they're doing. The acid and the base, they ionize themselves because they're strong electrolytes a lot of times. They will ionize. They just switch buddies and they go, huh, we're done. We're making salt and water. But the salt is not just like, oh, generic term salt, because we're very intelligent people and we know salt's not the same across the board. Sodium chloride is table salt, but every single ionic compound is called a salt. It's just another term for ionic compound. So let's do HBr reacts with, give me a base. Okay, I'll do lithium hydroxide. Thank you, Kevin. This H has a positive charge if you ionize it. What does the Br have? A minus. The Li has a plus, and OH minus. OH has a minus. So I put parentheses around the OH so that you keep it together. Don't pull it apart. All right. So when I make the salt, I know that it's going to be the 2 partners switching, but which one do I write first? I have to write the one with the positive charge first. So this is X. Well, hold on. Y. See Y. Y. Y comes first because it's the cation. And then, yeah, bromide comes second. So lithium bromide and what? Water. You see the H left and the H left? The stars because it looks like minuses. There we go. And then HOH. You can see that is just hydroxide bond with the hydrogen. So is it balanced? Balanced, yeah? No? Yes, it is. Cool. All right, so this will like to let you put this in the door. Okay, I just said that for you guys. I'm not sure. You should have listened. You said it. Okay, that was very unsure of myself. Okay, so you can see that this is just an acid-base reaction. We have our acide down here. We have our base, base, up here. I just made that up. I'm not sure if that's right. So they come together. You can see some of the ions. There's a H3O plus down there. It's really hard to see, but there's a red ball with 3 white balls around it. And then now there's just a red ball with 2 balls around it. Water, Mickey Mouse. And the other ions come together. But you don't see the ions actually together as a salt now, because what do a lot of salts do in water? They dissolve. So they come together, say, okay, we're a salt, and then they just break apart. So when you look on the molecular scale, sometimes it doesn't look exactly like you think it is, but you can actually go back and write the NIE and solve for that. All right, so here's you. Hydrochloric acid reacts with sodium hydroxide. Write this on your paper. And tell me if I'm right. Did I write down some of these on your leg pants? The paper I gave you? No, I'm not that good. I'm not. No. I just thought I'd be nice, but I didn't. You can write these down anywhere, okay? So shout them out for me. HCl. Darn it. Hydrochloric acid is HCl. Okay, what else? Okay. Yields. Reorganize it in your head. I will write down the pluses here for you and the minuses. All right, so I heard NaCl and HOH, water. Okay, so we are going to see water a lot of the time, so we may or may not see it all the time because it depends on if we choose the base with the hydroxide in it. Do you see that? See the second reaction doesn't have a hydroxide in it? It's going to yield a neutral compound. It's just not going to be water. And that's okay. It's still an acid-base reaction. Okay, hydrochloric acid. HCl, sodium bicarbonate. HCO3, good job. Because the H is bi, which means it just means there's an H. All right, so when we yield this one, we have a positive and a negative. This positive stays here. What's this big thing? The entire thing is negative. If you have to put parentheses around it, go for it. You just need to keep it together. Okay, so now what's it yield? NaCl and so H2CO3. So those 2 H's come together, right? This is really unstable. This what's that called? Carbonic acid. it doesn't stay in solution very well. So who's ever had carbonated water? You know, like the flavored ones? There's bubbles, right? What are the bubbles? They're what? Carbon dioxide. So this actually further breaks down, just this one further breaks down to water and CO2. So that's why your water tastes like water still, because if not, you're drinking acid, right? Nobody wants to do that. So we have our water still, and the carbon dioxide make it bubbly.
So if you write it like yields H2O and CO2, would you count it?
I would count it right. It's good. So I would take either this plus this or NaCl plus water plus CO2. It's either way you write it. All right, nitric acid. HNO3 plus magnesium hydroxide. MgOH2 yields MgNO3 2 because of the crisscrossing of the charges. HOH balance. Fix it.
2 in front of the
2 in front of the HOH, and is that it?
2 in front of the HNO3.
Right, because I have 2 NO3s over here, so I need a balance putting over here. Thumbs up if you like neutralization. It's cool. We're good with BCEs. Some of us might need to work on our nomenclature a little bit more, but you guys have some of these on your problem set 19B as well. All right, so what if I reverse this reaction? What would be in the reactants? Like this one right here. What would be in the reactants? Huh? If I reverse the reaction, then I'm going to take the products and put them over here, put these guys over here. Okay, so water would be in the reactants, right?
Oh.
Okay, what's the word for water breaking stuff apart? You guys know what does the lysosome do? Breaks things apart. What does Lysol do? Breaks apart, kills germs, right? What do you think hydrolysis means? Hydro means what? Water. Lysis? Water breaking apart stuff. Awesome. Opposite of neutralization. Water reacts with salt. Water says, hey, salt, I'm going to break you up. Boom. Breaks it up. Huh? Yeah, this is the last flap. I'm sorry. The first flap was the neutralization flap. The second, or now the last flap, is a hydrolysis flap. And so it's just simply the opposite reaction. So if you know neutralization, then you are awesome with hydrolysis. Hydrolysis just actually means water is going to be used to break things apart. And the salt happens to be what we're breaking apart. So I'll give us a salt, sodium acetate, NaCl2H3O2 plus aqua yields. So you guys tell me what you think it yields. It says acid and base, right? So what do we know has to go in the front of the acid? An H. Well, where's the H coming from? Uh-huh. Where's this H coming from?
It comes from there because it's yielding.
Okay, so it's yielding acetic acid. I heard hydrogen acetate. Sorry, I was misunderstanding what you're saying. So this H plus and this OH minus are going to break up, and this Na plus and this C2H3O2 are going to break up. The H bonds with that one, so C2H3O2, and sodium bonds with that one. All right, is acetic acid a strong acid or weak acid? Why is it weak? It's not one of the 6, right? It's not one of the 6, and everything else is weak. I can give you dinosaur acids, and they're weak, okay? Because if it's not part of the big 6 ones, then you have to call it weak. So that's a weak acid, and this is a strong base. What do you think the pH is going to be about? Acids and bases don't always yield neutral pHs. That's a weak acid, and that's a strong base. So higher than what? Higher than 7, right? So you just say it would be a basic pH, because that's going to win the war with the acid. Does that make sense? Okay, yeah. That would be neutral. And if you had a strong acid and a weak base, it would be acidic. Okay? So you guys are doing a lab with that pH part of it tomorrow. All right, so let's do these couple. And I don't write out water. I just say hydrolysis of blah, whatever the salt is. So let's do calcium phosphate. Hydrolysis of calcium phosphate. What are the reactants? Say it out.
2.
I'll wait. 3.
PO4.
Thank you. Not done yet. 2. Thank you. So calcium phosphate, CH3, PO4, 2. Plus HOH. I just prefer to write like this because I can see the rearrangements. You guys write it whatever way you want to. Yields. All right, let's mark our positives and negatives here. I know water has a plus here and a minus here. Calcium has a plus, phosphate minus. So calcium gets with OH, so CaOH. Is that good? 2, thank you. And H3PO4. Where's that 3 coming from right here? Phosphate's charge, right? Every single time, what have we done in our head? Crisscross, crisscross, crisscross. I should make up a rap for that one too. Okay. What is, I need to balance, so I need to put some coefficients up in here. Okay, so I heard 3 in front of the HOH because you said that 3 there. Okay, what else?
And 3 in front of the calcium.
So this 3 calcium here, I need a 3 calcium over here. All right, how many, see I've got 2 phosphates here? 2 phosphates, I only have how many phosphates over there? 1. So I need to do what here? 2 here. Well, guess what? That screws up my H's. Now I have 6 H's here. So I need there. I need a 6 right there. Alright, so now I have 6 hydroxides, right? How many hydroxides over here? 6. 3 times 2 is 6. Yay. So that one was a hard one. You had to balance a lot. Let's do lithium nitrate. Alright, lithium nitrate plus HOH yields. I heard it, HNO 3 and
H or LH?
huh? Li what? OH. Okay. Label these as strong and weak for me.
That's strong.
What's strong? Strong acid and strong base. Therefore, neutral pH. Let's go back up here. This is a, yeah, that's a base. Strong or weak? Strong base and weak acid. pH? Basic. It's above 7. So pH is above 7. pH is equal to 7. So litmus paper would turn what color for that one?
Red or blue.
Make a choice. Red to blue base. Okay, right there. Who feels good about reactions? Okay, some of us take part in my surveys. If you don't, I'm just going to assume yes. Okay. All right. Oh, we're not going to do hydrolysis right now. All right, because I'm saving all our activities for tomorrow, unfortunately. All right, so write the equations for the following. Go for it. You've got 4 reactions, 4 minutes. Write them someplace else. 4 whole minutes. Oh no, forgot I'm videoing. All right, you can keep going. We had done the first 2 already, and I didn't realize that until I was like halfway through it. But let's do the 3rd one for sure. So sulfuric acid, H2SO4 plus sodium hydroxide yields.
Na2SO4.
Right, sodium sulfate, Na2SO4, and HOH in balance.
2 on the HOH and 2 on the NaOH.
2, 2. Beautiful. All right, I see a couple people still writing. Yeah. Yeah, always have to balance them. Oh, and then let's do the strong weak. Is this that's not right. This is what I want to do. I haven't done this part yet. This strong acid or weak acid? Strong acid. Strong or weak? Strong base, right? Guess what we would call the pH of the salt solution? neutral. A strong acid and a strong base make a baby neutral salt. Okay? So a strong acid and a weak base make what kind of baby salt?
Strong acid and base.
So strong acid and weak base make what kind? An acidic salt. And a weak acid and a strong base makes a basic salt. Basic white club salt. There you go. Okay. So reactions are not so hard. Hopefully we are okay-ish with that. I am going to have you pull out your problem sets because I want to look at some of those too. But before we go there, I'm going to leave that there for a second just in case you need that. Sorry. I don't always realize how fast I am, so if ever I'm going too fast, just go, Priscilla, hold on. I'm very receptive to you telling me you need more time or questions. Okay, unicorn. Just say unicorn, I got you. Means I'll stop.
Why does that be uniform?
Yeah, I just thought of that. Okay, so this is a titration. The titration is a method of analyzing stuff about acids and about bases. Specifically an acid-base reaction. What's that called again? What kind of reaction is an acid-base reaction? Neutralization, right. So it's called a neutralization reaction. And it's because as you go through a titration, if I'm starting off with a pH way down here, what do you think I'm starting off with? An acid. If I'm so the way a titration is set up, I don't have a beer out with me right now. I'm starting off with a flask, and I put a burette in it, and the burette holds one solution. So let's say it's going to hold the base, and this guy down here is going to hold the acid. And it's just, I'm adding acid and base together, and I'm just going to put them together, which is a neutralization reaction, making salt and water. As I add base, why is this going up? It's not weakening the acid so much. It's okay. So they're neutralizing each other. The pH is increasing because I'm adding something with a very large pH, like a base, right? So if I start with a pH of 1 and I add exactly 40 milliliters of sodium hydroxide, you can see the axis down here says sodium hydroxide. If I'm adding 40 milliliters, I finally get to a pH of 7, which is my neutralization point. The neutralization point has a special name called the equivalence point. Did you define this in your vocabulary under your reading guide? Did you see that? Because I told some people to do the vocabulary differently because you guys left at different times. But underneath the neutralization foldable, I need you to write down something about the equivalence point. Okay? So someplace write down like a definition of the equivalence point. Whatever. I've already videoed my titration notes for you, but I'll go through some of the titration notes now because I've got a little time. I expected that first part would take us a lot longer. So I'm going to go ahead and explain some of this now. So under neutralization, put something about the equivalence point. So just like neutralize. You can, what do you mean? Copy what? No, do not copy those numbers. And then I'm going to pull up the actual other notes for a second too.
Just when it has a pH of 7.
Yeah, well, that's only, why would it have a pH of 7? Because what have I added together? It's not just a base and acid, a strong base, a strong acid. If my equivalence point was at about 9, what do you think I added together? Right, my pH was about 5. What do you think I added together?
How would you define? So what is?
So I'm pulling up these other notes for you. The equivalence point truly has a definition. I didn't save those notes very well. Has a definition of moles of acid equals moles of base. So when I say moles of acid are equal to moles of base, I don't have to say they're strong or weak. It's just the point at which they're exactly equal. Well, if I have a strong acid, strong base titration, when they're equal, they yield a pH of 7. But when I add them together and it's higher, maybe at a pH of 9, who was stronger in this case? The base, right? The strong base was added to a weak acid, and opposite if the pH was lower. So you can look at the exact point where they're equal, and you can say, oh, this was an acid that was strong and a weak base, or vice versa. So when they're exactly neutral, then that's a strong acid and a strong base. And I drew it like this on that graph previously too, because I had a strong acid, strong base titration. Yeah.
What happens if it's a weak acid and a weak base?
It forms something called a buffer, which we're not going to get into. Right, Alyssa? Yeah, you don't want your buffers yet. But yeah, they're just a little bit more complicated. It depends on a lot. They're Ka and Kb values, actually. Okay, so you realize that once I'm here, I'm at my point where it's going to start to get more basic now. So here I've got a lot of acid and not so much base, right? What about up here? Right, I've got more base and less acid. So who's my limiting reagent down here? The base, thank you, because I have less of it. Who is it up here? The acid, because I have less of it. Here they are exactly equal. All right, and so when you go through this, you can like not listen to all the front part of this notes. This is called volumetric analysis. In the volumetric analysis, it just means I'm using volume and I'm analyzing something with it. So this is a burette, and what you do with the burette, I'm going to pretend that this is a flask now. Okay? This burette has little graduations on it, like a graduated pipette or a graduated cylinder. So it actually goes up to 50. You read it backwards. So if I put sodium hydroxide in here, let's call it 1 molar sodium hydroxide, I can add it in here. So if it starts all the way at the 0 mark and I add down to here, that's the 10 milliliter mark, I read exactly what it says, and it says I've added 10 milliliters. My previous example, where was the equivalence point volume? 40. So I would have to add all the way down to here, and I would have added 40 milliliters. And once I've added that many milliliters, I would be right here at the equivalence point for what I was doing. Okay, so I've told you volume and molarity for the sodium hydroxide. I know everything about sodium hydroxide. So when I know something about it, I know both the molarity and the volume, then I call it the standard, the known, or the titrant. It has 3 names. If I know everything about one of the reactants, I call it the standard, the known, or the titrant. So the other one, the acid I may not know everything about. So in this case, my acid is called my unknown, or my analyte. That only has 2 names. Okay? So that you're going to have to like identify things in questions where you read something and you say, oh, I know both molarity and the volume about this person, so this is the standard. And if you only know, let's say, all you know is the molarity of this acid, all you know is the molarity of the acid and you don't know the volume, then that's what you're going to solve for. So that's your unknown because you don't know everything about it. So I'm going to make up a question for us because I want you to try this with me while I'm here. So if I have a reaction between HCl and sodium hydroxide, and I'm telling you in the problem, for this titration, I've had to use 1 molar sodium hydroxide, and I used 40 milliliters of it. I was titrating this sodium hydroxide with 0.5 molar HCl. How much volume do I need to neutralize to the equivalence point? What did I say was true at the equivalence point? Right, so when moles and moles are equal, I can convert between the two with the mole ratio. Remember stoichiometry? You did like moles over liters, and you times it by the mole ratio and cancel your mole ratios out. It's that we're back to that again. But they're pretty simple, okay? So the first thing you always do for these types of problems is when you're reading the question, write down the information about the 2 reactants underneath wherever you write them. We also have to finish the BCE, so let's finish that first. And HOH. Right. So that was basically telling me it's a 1-to-1 mole ratio between the acid and the base. So the way you start these problems are, I'll give you this hint right here too. You guys might want to go ahead and write that down. Then I'll finish that off. Or take a picture, whatever you need to do. You need something for reference. And this is kind of like a flow chart for me. I'll explain as I go here. You take the volume of your standard, which were the other 2 names for standard, known and titrant, right? So you take your volume. How do you get to moles if you know the molarity? You guys remember M times V? Remember this? Yes. M times V equals moles, okay? So if you have this information, volume, and you have the molarity, because you know everything but the known, you can multiply them together, you can get to moles. So once you get to moles of a hydrant or standard or known, whatever you want to call it, how do you get to the unknown? How do you get from moles to moles? Yeah, we're assuming they're equal there, but we need to use the mole ratio to convert to the other identity. So to convert out of, let's say the standard in our example is sodium hydroxide, and I want to get to moles of the unknown, I'm going to use my mole ratio to get here. So that means I needed a VCE to get that mole ratio. That's what we previously wrote that. And then once you get to moles of that, you can go anywhere. I can ask you to go to grams needed. So that's one option there to go to grams for moles. Or I can ask you to go to molarity. Molarity's units are? Over liters of solution. Okay. So once we get to moles of our solute, or our unknown in this case, we can divide it by the unknown's volume. We can get to molarity. And the example I'm using right now on the previous slide, I'm asking us to solve for volume. Well, how in the world am I going to get volume on top of a fraction? Anybody? It's fun. How would I get liters on top of a fraction? What's this? I flipped molarity. Remember, you can flip molarity upside down. The number still stays with the moles. So like molarity, if it's 1 mole, I put 1 mole in 1 liter. I can flip that, and that's what we're going to do in a second, okay? So let me go back here. I'm going to show you how to start the problem. So we're going to start with the volume and the molarity of the standard. So what's my standard here? Which of these? HCl or NaOH? All right, so this is my known, and this one's my unknown. Okay, so I'm going to start with my 40 milliliters, and I'm going to show you guys this method. You can convert 40 milliliters to liters, or you can just stick with the milliliters. I'll show you the liters first. So take that to liters for me. How do you do it? Right, move the decimal back. 1, 2, 3. So 0.0400 liters of the sodium hydroxide solution multiplied by the molarity. But I don't want you to write molarity as an M. I want you to write it as moles per liter. Okay, so 1 mole of NaOH per 1 liter of solution, or NaOH solution. So now, so far, my liters and my liters can cancel, right? What's my next step according to what you just wrote down?
Do the ratio.
Mole to mole, so mole ratio, right? So my question was to get the volume of HCl needed. So I can stop here and go, all right, let me get rid of moles of sodium hydroxide. I don't care about that one. I want to get HCl. I've got a 1-to-1 mole ratio up here. So what goes on bottom? 1 mole of NaOH, and what goes on top? 1 mole of HCl. Now I have moles of NaOH gone. Now I want to get to the volume needed when I have available to me 0.5 molar HCl. So how did I just say that we can, what did I just say we could do with molarity? We can flip it. So let's write this flipped. 0.50 moles per liter, 1 liter. The number stays with the moles, okay? Don't put it with the liters. So that 0.05 moles is going to go down here. Why am I putting it on the bottom anyway? Right, so you can cancel out moles of HCl.
Why is it 0.05?
I just randomly put 0.05. It's 0.5, sorry. Thank you. Because I would have calculated it wrong too. 0.50 moles of HCl, and then 1 liter on top. Calculate. I believe you. Oh, 0.08, so 80 milliliters? Yeah. Okay. So 80 milliliters, which is equal to 0.08 liters. So in our problem, if we were actually doing this titration, we would need to use 80 milliliters of the acid, and we would need to use 40 milliliters the base. Well, you see 80 and 40, one of them's 2 times the other, right? Well, does that make sense with our molarities? See how this molarity is 25 and that one's 1, so 2 times that one gives me that one, right? This one makes sense because if I have twice the concentration, I only need half the volume. Does that mathematically make sense to you? And that's only true because they're a 1-to-1 mole ratio. So you can always check some of these in your head and go, oh yeah, that makes sense. Okay? Alright, so I'm going to give you guys a couple minutes to actually start the second question that I have already solved on my video, so you can watch the video. It is right here. Student titrates 20 milliliters of sample of hydrochloric acid. The titration requires 20.05 milliliters of 0.1819 molar sodium hydroxide. That is the molarity of the HBr solution. So I recommend you do the thing that we just did. I recommend you write your BC out first, label your M and D for both of them, and then start. Go for it. I recommend paper for this.
So the napkins are the type of go to last year. So there's the I know, but it's weird because
As you write it out, you kind of analyze it as you go. And now I'm thinking, I'm going to lie to you. Oh yeah, I got this. Right here. So the 1 through 3 samples I solved in the video, and I'll actually ask you guys to pull your phones right now. Actually, the video pulls up for you on your phone. It's under the homework, the link. While you're starting it, pull out your phone and get the Wi-Fi started. The other here, the U-Try one, you have to use those times. You have 6 problems to do right now, and you have 45 minutes. So you can see this. 6 problems, 45 minutes. The first 3 are lecture ones, and you can watch them on the lecture notes with me, and do them with me on the lecture notes because I videoed it already. Or you can start it and then go and check it. So if you go under my homework website, under tonight's homework, I put part 1 video and part 2 video. The first video is 15 minutes and I solved both problems 1 and 2. The second video is 6 minutes and I solved number 3 for the lecture problems. Yeah.
so the problems are on the video.
Yeah, I solved this one, and this one on the video. And then I give you a couple hints about these, but you guys are doing these as well. So these are your U-Try ones. Perfect, thank you. So go ahead and do that. I have somebody coming in here in just a minute. But I'm also putting this video up online too, so